Thank you. And Dan, thanks Dan for this switch, because he now has given me the opportunity to do the favor that he did to me yesterday. And in the hurry of not being late for the lunch, I forgot to say something. What I wanted to say really from my heart. That I'm very happy to come here as ever, and it's very nice to see. I don't know whether this logic circle is there in other cities or not, but this effort of Mir Babu and his friends and colleagues and students really commendable, and it has fructified into this Society for Logic. Very interesting. Though what I might say at the end of my talk will make me a heretic, because I will say that we should go beyond the logic, etc. So yesterday, the basic point I made was that computation is, or rather computability, as an informal notion. Of course, it has been there since millennia. And why was it? This is a question that you can ask, and the answer is simple. That at around the same time, roughly same time, so many people came up with the equivalent notion of computability, formal notion of computability, right? So that's at least history of science question, and we are just discussing in the break that why, if you ask this question, what makes some discovery happen at some point of time and some place and not others? So notion of computability, as you know, in Russia, Kolmogorov, in America, Post, in England, Turing, of course, in Germany, Gödel himself, they all came to definitions which are more or less, why more or less? They're exactly equivalent. It so happens that I think the Turing's notion is possibly, in some way it is very easy, his formal notion of computability, and therefore subsequent development, computational complexity, that uses Turing's definition and not the rest, right? So I said that from the informal notion of computability, one can come to very easily a specific problem, which is undecided, right? The halting problem. And the proof that is given in the slides is just a one-slide proof, and you can see that we did not use formalization anyway. But if we want to go beyond, how do we prove some questions, some problems to be undecidable in some other domain? In fact, Turing had to prove that he proved the undecidability of the problem of logic, which Gilbert asked, given a first order sentence, basically given an algorithm such that which takes as an input any first order language sentence and decides whether it has a proof or not, whether it's a theorem of the logic. Which of course known by this phrase, N-Logic's problem, and this was done. Turing actually did it by proving that halting problem reduces to this problem of deciding the satisfiability or validity of a first order sentence. Uh, it is here. How did he prove this? And in fact, that's why we use this machinery of Turing machine. And this is where the formal notion of computability was needed. And before that, so what is this formal notion? So there is this informal notion that what is an algorithm, which everybody kind of knew. What I'm saying, it's a very clear notion because given an algorithm, there was never any doubt whether it is an algorithm or not. Right? Whether you call it effective procedure, mechanically definable, whatever term you may use, given an algorithm, you had never any question whether it is an algorithm or not. So positive results could go through without any problem. But if I wanted to show that there is no such algorithm exists, and that's where we needed a formal notion. Right? So basically the thesis says, Church-Turing says, that for every algorithm, now this is an informal notion, algorithm, there is a Turing machine that simulates A, and therefore the function computed by that algorithm or the computable set defined by A is the same function computed by the Turing machine. A more succinct statement is, if a function or a set is computable, then it is Turing computable. I'll come to this thesis a little later when I'm talking of a slightly more general thing, but this has been criticized in both directions, that this thesis is too weak or too strong. Now, there is also a notion of extended Church-Turing thesis, and which we'll discuss. That this thesis is not a mathematical statement. Although, by the way, there are some proofs which claim, by very famous logicians like people like Andreas Blas and Gurevich, they claim to have proved Church-Turing thesis using a notion of algorithm, which they claim is the most general notion that can be given, right? Evolving set algebra. And so there is some claimed proof of this, but in general people feel that there cannot be a mathematical proof because it is relating an informal notion to a formal notion. And yet this thesis really cannot admit a proof, and there are wide discussions why we accept this thesis to be true. But given that, so let us now say that we all believe, I'm sure in this room all of us believe that Turing computability defines computability. Right? So Turing's proof of undecidability of first order logic, essentially what it did, in fact we have been seeing examples of this, that it expressed, given any Turing machine M and a string X, it expressed this sentence, M accepts X, in the language of first order logic. Right? We have seen, Jam gave examples of such writing things in first order logic. Now, I just wanted to say, so the way I'll give a little idea about that, how you write that sentence, but I should say more that Egon Borger actually provided a minimal, so this is called a logic implementation of Turing machine. So Borger gave a minimal implementation scheme. By that what it means is, normally most of these, when you try to express something like M halts on X, the sentence that you write, the models of that sentence will be categorical, quote unquote categorical. That means that it will exactly mimic the computation of the machine. Now that, for example, suppose in writing this, normally you would say that at any given time, the machine is in exactly one state. This is the kind of thing, those of you who have seen the NP completeness proof, you will see this is also translated as a propositional logic problem, this particular part of the implementation. Now this is actually not necessary. So I can admit models in which there can be at the same time lot of states will be true at the same time the same cell have a number of you can admit that the cell has any number of or some number of symbols, and yet the thing goes through. So that is in fact once you have that minimal implementation, then a whole lot of theorems which were proved since 36, they come as kind of corollary. So of course Hilbert's Scheidung's problem, then NP completeness of the satisfiability problem of propositional logic, then undecidability of satisfiability of first order formulas in finite domains. See, Trachtenberg asked this question that what if I want to know whether a formula, first order formula, admits a model, this model has to be with equality as a logical primitive, that this has a model which is satisfiable only in a finite domain and not not necessarily in an infinite domain. So this is also undecidable. Then there is a notion of spectra. So which means I give you a first order logic, and now I ask a first order logic sentence, and I ask what is the set of numbers which are the cardinalities of the finite models satisfying this particular sentence. So that is called spectral problem, and there is so all these theorems actually come out as corollary of one, if you say, expressibility result. And I've given the reference there. So basically this, I want to say that D is a Turing machine and X is input. I want to express this in logic that D accepts X or D also on X. And this, I'll not go too much into the details, but there are two kinds of, you can see that the formula that I write, will be conjunction of three things, alpha, pi and omega, and they use four predicates, Q, C, H and S, and intended meaning is that Q, IT to be true means that at time t the machine D is in the ith state, and similarly C, I, J, T means at time t jth cell of D has the ith symbol, H, J, T means D is scanning the jth cell at time t. This is just the successor, that is B is the successor of D. Okay. So these are the predicates, four predicates, and out of which you create this alpha, pi and omega. Alpha asserts what holds initially in the computation D on the string X. In other words, alpha asserts the initial configuration of D on X holds. Pi is the conjunction of some two groups of formulas, essentially the program of the Turing machine. That's what you are saying. So pi is doing that. Basically it is saying that, let's say put the pi or formula, what it means is that if some configuration is true at time t, then if you look at the computation of the Turing machine at time t plus 1, it will have another configuration. So basically it is saying that this group of formulas, making sure that the model, in that model, that next configuration also will be true, etc. And omega is the termination condition. And because of the minimality, we don't say that there exists a time when the halting state is reached. What we rather say, and this is a clever thing that Borger realized, instead of saying that, you say that there is a time where no state other than the halting state is true. So which effectively means the same thing, but categoricity is not required because of this. Okay. So this is the kind of formula. So essentially, if you see this, that this is saying that if at time t it is in state R and it is the head is at cell J and the cell S, whatever, J cell contains the SH symbol, and then T dash if it is the successor of T, then and J dash is the successor of S, then it is saying what happens, the quintuple, it's a right move, it is 40. Okay. So this is the omega formula that I was talking of. You are saying there is a time t that for all I is not 2. 2 is the unique halting cum accepting state. I is not 2 means the at time t the q predicate does not satisfy this. Okay. So this works. And there is a one slide kind of proof sketch. Next, so my point is in the so-called ontological analysis of computation, I see first the formalization of computability as one entity, then the relationship that it has with various logics, that is the thing that we talked of by minimal implementation of that model in various logics, that's one thing. But there is another step that is required, or that has come up, and that is the arithmetization. So arithmetization basically means that to view an entity in terms of natural numbers, arithmetic, and of course arithmetic is standardized, axiomatization is there, and now there are two senses in which arithmetization has been used. The 19th century sense, in which it came that basically entire analysis they made arithmetic. By that, what it means is that all the real numbers as well as the theorems of real numbers, most of the theorems, you could say in terms of natural numbers and sets of natural numbers, and even certain kinds of functions like continuous functions, they also could be done using, in this sense, arithmetized. And in 1930s, there is the new sense in which logic and computability, they were arithmetized. Logic arithmetization was done by Gödel, and I suppose, not exactly I'm saying that, but essentially this also came about at around the same time, once Turing machine came about. And this is the point, that it is truly remarkable that analysis and computation converges to a common source. By the way, this is one of the lifted sentences. I will give you the reference later. And computability plays an essential role in analyzing strengths of theorems of analysis. Right? So what is being said is that arithmetic is the kind of base thing in terms of which you can view real analysis as well as not just real analysis, analysis in general, as well as computability, and this helped in remember in the beginning I talked of classifying theorems, and as somebody has already read the book I refer to Stilwell's book that is about reverse mathematics, and so very quickly some things about arithmetization of analysis. You see, Poincaré said in 1902 that analysis today has only natural numbers or finite or infinite systems of natural numbers. So, in fact, this phrase arithmetization, you can see, mathematics, as one says, has been arithmetized. Now, you can see this, I just very quickly, integers. So, once you have natural numbers, you can see integers as a pair of natural numbers. So, the intended meaning of this pair is n1 minus n2, q the rational ratio of two integers, an element of reals as a set of rational numbers, which is of course cut. So sequences of reals, not sets, sequences of reals as well as real continuous functions are also represented as sets of rational. So essentially everything boils down to integers or sets of integers. Now arithmetization has a limit, and of course which came from Cantor's, that there is no bijection between any set and the set of all its subsets. Right? So clearly you can't talk of sets of real numbers or any property of real numbers in terms of this arithmetization project. Right? So again, it's interesting that this proof, all of us know this proof, that a set and its power set, they cannot be a bijection between them. That proof is diagonalization, and that really is the key proof that was used over and over again. And if I may say so, that entire recursion theory which Professor Chakravarti is going to survey is really to deal with very, very interesting ways of looking at or using diagonalization. They have this force saying that you have an infinite set of constraints, and how do you diagonalize over that, and all kinds of results, like the oracle result, that there is an oracle relative to which P is equal to NP, and there is also an oracle relative to which P is not equal to NP. All these are basically diagonalization proofs, right? So, I don't know how to say it, but it's a basically key concept, so I should mention that. So very quickly about arithmetization of computation. Peano arithmetic is the action system of arithmetic, and this fundamental result is that one class that you define using PA is this sigma 1 captures all computably enumerable states. So these will be, those of us who are not yet familiar with this term, this will get clear. I am just mentioning as a point that essentially a class that you define using Peano arithmetic captures recursively enumerable sets. And at one level it is so. On the other hand, this gives us also Lorentz incompleteness theorem, and also lets us capture computable analysis in terms of computable or recursive enumeration. So very quickly, language of EA is what? There is a constant 0, there are variables, there are function symbols, successor, addition, sum and product, relationship symbol, equality, logic symbols, the usual logic symbols, parenthesis, right? And you can use this language to define now new predicates or sentences. That is for example, this is the first piano axiom. You can now define the less than equal to in terms of the sentence of that or a formula of that logic of that system. And so you can, for example, make statements like there are infinitely many brides. So all these kinds of things you can express. And in particular, there is this class of arithmetically definable sets. They are basically any arithmetically definable property is. So firstly, what does it mean? This alpha is a PA, you can say, formula with one free variable, and which can be, standard thing that you can see it as some alternating quantifiers followed by these quantified variables and u, the free variable, right? And of course, you use the projection function. Using that, you can collapse, two or more same kind of quantifiers. So now we will have exactly, so the next thing is, so there's every arithmetically definable property is defined either by this type of formula, that there is a quantifier starting from for L, there exists, or it will start from there exists and for L. These are called sigma formulas, and if there are n alternating quantifiers, this will be sigma n, and this will be pi n, right? Where there are n. So the theorem is a set of numbers is accepted by a Turing machine. The set is therefore recursively enumerable if and only if this property is defining the set is in this class. So this is the main theorem. So in one direction it is fairly easy to see that supposing you write this. So what is the sigma 1 formula? Basically it says there is integer which is satisfying some easily checkable property, recursive. So you just start going through, just keep checking. This 0, does 0 satisfy? If not, 1 satisfy, and so on. So if a number satisfies, if this formula there exists n, this sigma 1 formula is true, satisfiable, then you will definitely find that it is so. Otherwise, this process will go on, and that's why it is recursively enumerable in that direction. The other direction comes from, let me just give you at least the way I see it, that the reason the other way, that is, given a Turing machine, what it is computing can be seen as a sigma 1 formula. That thing, that if we look at it, that there is a logical formula psi implementing the Turing machine M in a finite model, if and only if M accepts it. Right? This is something that we had seen, that is that implementation of logic implementation. Now, remember those predicates were there, Q, they're saying that at time t it is in this state, at time t the jth cell contains the SF symbol, so that was a ternary predicate. So there are some 4 predicates were there, but now since it is a finite model, all these predicates can be coded as integers. So essentially, what we can as something finite. So the idea is that we can try to guess or look for a number which codes these other 4 numbers, which these 4 numbers code those 4 predicates. So that's the kind of rough rough idea. Kind of doesn't really prove the on-leaf part, but some more work is necessary. But this is the basic idea. The arithmetization of TNs immediately gives us a proof of incompleteness theorem. If you see the incompleteness theorem inside the Gordon's original paper, you will see right in the beginning he gives a sketch of what is this proof. And then most of the paper, really he says that this particular predicate can be expressed in what is this thing? The primitive. This particular predicate can be is primitive recursive, right? Now, I mean, of course, primitive recursive, it is obviously computable, but we can, because today we know after that Church-Turing thesis, if he can do whatever he was doing, I can say there is a Turing machine to do it, and now you arithmetize. And so let me very quickly say this. This will take me. So let F be a sound. I mean, this is slightly stronger than what Gödel used. Sound formal system for arithmetic. Let this Tn denotes the nth unary predicate in the language of F. Sn denotes the sentence Pn applied to it. Right? Now I am defining a Turing machine D. This D, what it does, that on input n halts and accepts if and only it finds the proof of Sn. So what does it do basically? It just looks at strings in a canonical order over the alphabet of the formal system and accepts and halts if and only if it finds proof, of this sentence Sn. Now, from the arithmetization of D, this is where I am using the arithmetization of D. D defines a number theoretic predicate Qn. So this number theoretic predicate Qn holds if and only if Sn is doable. Now we will consider negation of that predicate Q. This, well, let's put a negation in front of Q. So this is also number theoretic, though this is not computable. This Q was computable, this is not computable. I mean, that's a side remark. Clearly, this Q is number theoretic and expressible in F, and now you get the contradiction. Let this be the Rth unary predicate. So this is also a unary predicate, arithmetic. It's an arithmetic predicate. So now point is neither SR nor negation of SR is provable in F, whereas SR is clear. So you see this, I use arithmetization at one point, rest is the standard kind of proof of diagonalization. Of course, it's very clever, etc. Only on Einstein I am saying this is only a diagonalization. But my point is only this, that you had that formal notion of computability, from there you had this notion of arithmetizing computability, and from there, Gödel's theorem came up. So this just was side remark, that this unprovable sentence SR is not interesting as a number theoretic. This is saying something about the formal system. This is, of course, proves something about the limitation of formal logic. Interesting unprovable sentences emerge when we expand to a system of analysis by introducing variables for sets of natural numbers. Then we can talk about real numbers, continuous functions, etc. And which of their properties are provable depends on which set existence action that we have. So there is some remarks about computable analysis. The point here is that computable sets are those sets of natural numbers for which the set membership decision problem is computable or decidable. So which really means this is precisely this should be intersection. This is not union. This is not union, this is intersection. Sigma 1 intersection phi 1. Right? Those sets which which are recursively enumerable and whose complements are also recursively enumerable, which means that you are talking of just the recursive sets. The simplest reasonable set existence axioms is that computable sets of natural numbers exist. What do you get out of it? Once you have this thing, then you get a system called RCA 0. I'll give you the reference for all this. The resulting analysis is called the computable analysis. Now, in this system, you cannot prove clearly the existence of sets which are recursively enumerable, but not recursive. But it cannot. But interesting thing that you cannot prove. See, this is maybe more interest to logicians, but to a mathematician, this statement will be more interesting. That this system RCA 0 cannot prove this theorem that limit for every monotone bounded sequence of rationals exists. So-called monotone convergence theorem. This cannot be. So this is an instance of incompleteness with respect to this system. So you can go beyond, of course, computable analysis by providing more stronger set axiomatizing stronger set existence axiom. And so essentially that is arithmetical comprehension is one that posits existence of sets defined by sigma and formulas for summing. So anything that you can define in the arithmetical hierarchy is admitted, any set. And this is actually strong enough to prove most theorems. This is not quite, it cannot prove well ordering, but other things. But at the same time, this thing of the importance of RCA 0, the one which is based on computable sets only, that it can prove equivalence of arithmetical comprehension with many separated results of analysis. So we see an intimate connection of computability with. Now I will soon get into your. I said 10 minutes. I will not give you this. So now after this, so something about church Turing. See, the interesting thing is this: that church, how did he? Turing came to this notion of Turing machine, as Jan said that all of us must read Turing's original paper. It's so readable. And if you see, how did he come to define Turing machine? He basically did a kind of psychological analysis, if you like, of somebody, some human, computing something, right? So he came, he said he reads paper. Now, of course, Turing is famous for reading, trying to find out the minimum that is required, right? So, many of you know, right? Turing did not use most of these things like soaps, shampoos, and all kinds of other things. See, if you see that same thing, basically soap we use for clothes. So there is one bottle soap we use for head. That is another bottle soap we use for body. That is another bottle or cake. So he wanted to have as few things in his house with which he can do things. And thereby, similar thing he did here also. What is the minimum thing that you require? So he said two-dimensionality of the paper is not important. So he came to K, Turing machine K. Now there is extended Turing. The interesting thing is computability. So now we have quantum computing, right? Which is not how humans compute. But even that does not go beyond Turing. So what is happening is did Turing capture something which is actually more natural than what he claimed? There is a notion of extended church Turing thesis that every quote unquote reasonable model of computation can be simulated by Turing machines using at most polynomial time over time. Now this implies if P not equal to NP, no NP complete problem can have a polynomial time algorithm in any model of computation. And therefore, the claim is P not equal to NP is universally true. And that since there has been really so much difficulty in proving or disproving this, so some people at least say that it should be considered a law of nature. And a little bit of discussion on that, or maybe I should point out a paper for that. And this is by Scott Aronson, and he discusses various esoteric models of computation, soap bubble, protein folding, quantum computing, quantum advice, adiabatic algorithms, quantum adiabatic algorithms, hidden variables, relativistic time dilation, analog computing, something space-time, some closed space-time, and all kinds of things that people you can think of. And this is very interesting. Anthropic computing. What does it mean? That given a satisfiable set of formulas, given a propositional formula, you guess an assignment. Now, if that assignment is not true, in that assignment the formula is not true, you kill yourself. Right? So, some condition on you are seeing anything or you are becoming alive, you have solved the problem satisfactorily in 2-3 steps. Right? So this is a notion of anthropic. So people actually discuss such things. So there are physical completeness of NP hardness assumption. What I'm trying to say that Church-Turing thesis is an extended version, and that relates to such statements. Once you accept the Church-Turing extended thesis, it makes non-trivial statements in physics. That there are no nonlinear correction to Schrodinger equation. Schrodinger equation is basically linear, and which people say is the problem. If there was a nonlinear term, then we can do much more. This is the other thing. Real numbers cannot be stored with unlimited precision. In other words, no bounded physical system can have unbounded entropy. So, there is a lot more once you accept a little more. Now I come to slide 8, still not in Jam's time, right? So this is what I wanted to say. Now there is something I'm shifting here. There is this notion of theoryful versus theoryless. Let me see what I'm trying to do in this part. That we are very familiar with formal system. At the same time, we have seen various limitations of formal system, undecidability, incomplete. Right? Now, roughly what is being said is that formal systems, of course, are very powerful. I mean, so many things are based on formal systems and computer algorithms, which are also often based on some theory. So he says that there are really two kinds of things, theoryful and theoryless. Right? So those aspects of knowledge for which there is a good predictive theory, a mathematical or a scientific one, is Valiant is terming such knowledge as theoryful. The rest is theoryless. Now what is rest? In fact, rest is most of the human being. Recognition of objects and scenes, language acquisition by children. Even when you manage your finance, most people manage their finance, but they are not economic pundits. So, you see, all these human behaviors are highly effective without basing their action on any theory. So they somehow manage to cope. And if you see, the entire evolution is about coping. And the machine learning credo, or Valiant's credo if you like, the coping mechanism with which life abounds are all the result of learning from the environment. This learning can be done by concrete mechanisms which can be understood in terms of computation, possibly it is a little more general. And this general sense needs to incorporate an algorithm that can evolve. This is where we need to kind of depart from our standard notion, the informal notion of algorithm that we say it's something fixed, there's an input coming, there's an output. I mean, if you really try to see the computational process of these coping mechanisms, you see the algorithm is changing, what is input is not clear, and so on. And even what is output is not clear. And at the same time, something really happening which is highly reproducible. So learning is the ability to generalize. This is understood. And generalization is induction. Okay? So I'll just go over quickly that Aristotle had spoken of that you come to a belief either through syllogisms or through induction in mode of acquisition. But clearly, what does induction mean? I see some limited instances and then I make a general statement. Now look at this. This is about 1800 years ago. I suppose Roman philosopher, he said that the dogmatists claim that the universal is established from the particulars by means of induction. If this is so, they will effect it by reviewing either all the particulars or only some of them. But if they review only some, then their induction will be unreliable, since it is possible that some of the particulars may contradict the universal. If on the other hand their review is to review all the particulars, theirs will be an impossible task, because particulars are infinite and indefinite. There is, by the way, it is interesting that kind of same thing is being said is in a theorem which is known as no-freelance theorem. There is no quantitative theorem. The name is interesting, so I thought I should say it. Now, how do you resolve this problem of induction? So, firstly, he makes this point, this is clear. On the one hand, if no assumptions are made about the world, then clearly induction or generalization from a limited number of observations cannot be justified. On the other hand, successful induction abounds all around us. By that, what he means, the children, they see few examples of, let's say, balls and apples, and yet they can distinguish very quickly between balls and apples. Both are red and spherical. So, the point he is making is, Valiant says that for a computational account, it is not necessary to aim to capture induction or its derivative. He says this thing somewhere that Turing did not try to capture the notion of computation in all its generality that humans can do. But what he tried to generalize or put it in a formalized way was something which is universal and reproducible. So in that, once you accept that, then you don't have to really you see, Kepler also came to discover laws of planetary orbits through generalization. But your theory need not, or whatever you call it, computational account need not consider that, because Keplers are not happening every day, right? Now, according to Valiant, there are only two assumptions suffice to rigorously justify the highly reproducible, naturally occurring induction. So I'll not go through these things. They call invariance assumption and learnable regularity assumption. But the interesting thing is this example you look at. Suppose you are presented with an urn containing millions of marbles, each one with a number written on it. You can draw a marble uniformly at random from the urn, one is allowed only 100 times, 100 draws. The task is to determine which numbers occur as marble labels. Clearly, if all the labels are distinct, then it is impossible, this task. Trivial if all the marbles have the same number. But what if there is only a fixed number of marble types? Let us find. Now there are two sources of errors, as you can see. Rarity, that as you are picking, some marble types are so rare that it's very, the chance is very, very small that your draw will pick up such a type of marble. And the other is ill luck. Something might occur with large numbers sometimes, but when you pick your 100, you have been very unlucky that type you could not draw. So there are these two sources of error. The point is, there is some working out you can do, that in this case it is possible to say this, that assuming that there are only 5 types of marbles, you can predict with 97% confidence that after 100 draws, you have seen representatives of at least 80% contents of the urn. Now, this urn example uses both of those assumptions. It can be shown. But the point is this, what kind of result that you get? And this is what we call probably approximately correct. There is this, you are getting this only with certain probability, whatever statement you are making. That is because that there can be, this is the ill luck kind of error. The other error is there can be rare type error. So that gives you an approximate answer, and this gives you a probabilistic answer. So that is why this kind of learning is called probably approximately correct, and it has been termed as fact learning. So just one second, and this is the final thing. And it's interesting that both Turing and von Neumann, they believe that biological and cognitive processes should be viewed as computation. And both shared a second crucial insight. By the way, this view is again from Valiant. That mathematical logic from which computation theory had emerged was not the right grounding for a computational description of either thinking or life. In fact, this is Turing's own words. After discussing non-computability results in logic, Turing in a 54 paper had said, the results which have been, this is what I am reading, the results which have been described in this article are mainly of a negative character, setting certain boundaries to what we can hope to achieve purely by reasoning. These and some other results of mathematical logic, I think he is alluding to Gödel's incompleteness theorem, may be regarded as going some way toward demonstration within mathematics itself of the inadequacy of reason unsupported by common sense. This is very interesting. He is not seeing incompleteness result as some kind of barrier. He says that, look, you have to have, of course, you have to be reasonable, you have to have logic, but you need to incorporate common sense. So, supposing, what is this reason plus common sense? So the point, I am coming back to the old thing that we said, that pure reason, syllogistic mode of discovery of knowledge, suffices for theory full. However, mathematical logic has its limitations. A priori, this reason plus, that is reason, formal logic, etc., plus something else, so called what Turing said, common sense. you know, they can transcend these boundaries, these limitations. So now what is that notion of algorithm? That, you know, that is difficult. So couple of words about references. This is the book. Much of the previous first part was from here, Stilwell, reverse mathematics. Then, first, philosophy of computer science, entry in Stanford Encyclopedia of Philosophy. The very first few slides were based on this. Gordon's incompleteness theorem for undergraduates. I wrote up something long back, and the reason is to teach our PhD students at Kanpur. So this is, I'll share this with you. NP-complete problems and physical reality, Scott Aronson. This is, of course, this back learning, probably approximately correct. This is a book by Leslie Bullion. And this is the problem of minimal logical implementation. This is not a book, I mean, this is a paper, Egon Borger. Thank you.
Thank you, sir, for your valuable talk. Now, I would like to request any question?
No, I think Dan is there. My God.
Do you have any question?
Thank you very much, Professor Vishwas, for coming over here, and we are very grateful to you. You accepted our request.
No. This
very very nice, beautiful lecture. So,
I'll leave the slides with a copy of the slides with Castro and some of these notes that we have.
so from our side, as organizer, we have some, something for you. So I'd like to, I request Professor Me Chakraborty to please hand over this thing.
We can have it later, because I think I've already taken time from Jan, and I really wish with also Logic Circle to look at these new problems.
Thank you very much, Mark, for this wonderful finishing and the beginning. So here is something from our side,
Yes.
from the organizer side. This is photogenic. This is waterfall by Shorno Potwa. Shorno Potwa is very famous. You can go to Google and see. And there now in Kolkata there is some workshop going on. And we just got the chance to take this from her directly. I mean, so it's the original stamp. So she draw this painting picture from there. So
Thank you. This will be our editing.
Thank you very much.
And thanks a lot for asking me to give this talk. I did a lot of reading. I don't know how much I have been able to convey, but at least I don't know about the audience, but this has made some kind of intellectual progress for me. And thanks a lot.
So our next speaker is Professor R. Ramanujam. So yesterday also gave a talk. So I request Professor.
The part where common sense is missing. So, and
return to thinking about these things. From that, spoiled it for me now. My mind is full of learning theories. Yeah. Okay. There is this theorem that we said, we talked about yesterday, as this connection between automata, and this is a statement that if and only is definable by sentence. Automata is not a logic order with symbols for unity predication. Now, what was the logic that we had? We talked about this. Is that first you pictures alphabet finite set and E finite set, and you have unary predicates, and you have first order variables x, y, and so on, and then set variables which are predicates, and then so you have atomic formulas of the kind that this element is set, and then you have equality. These are your atomic formulas, and then you close under negation, which is junction, quantification, and over set point. This was the logic. And so what is the, how do you give semantics of this logic? You are interested in your notion of behavior are finite sequences over the finite set. Well, negation is so for all x alpha. So this is the first order elements, and these are the second order elements. So this is quantification over elements, and this is quantification over sets. X is a set of elements. So I could change. Right. So little x and big X, yeah, and little x an element of big X. Yeah. So now, what is the structure for this logic? Remember we said, suppose you have A belongs to Automata, and we associate such structure with it, which is the element set 1 to A. These are your positions on which the order relation is a natural order relation of natural numbers, and now you interpret the predicates, which let me use some A. What are these? So these are all sets. Right? These are unary predicates of the sets. These are set of all j belonging to A, such that all the positions where A occurs in this world. Right? So that is the interpretation for every unary predicate that you have got. And now, if I am talking about a formula alpha, it has some first order variables and it has got some second order variables. Right? If you talk about the free variables of alpha, so let me call them Fv of alpha and Sv of alpha. I don't know what to use. I might as well use this notation because I think we should follow the presentation here. So you have the first order variables and second order variables, and then you can talk about a structure. Now you have the structure. So what is your model? A model. So if you have alpha, let's say it has three variables, x1 to xm, and second order variables, big x1 to big xm. So you are now talking about a bunch of elements v1 to vm, interpreting the first order variables, and n sets given to you. So let me call it big D1. So this is your model. When you are looking at a formula alpha, you are looking at a model of this. Now, I should really write it as an interpretation, which is what you do the notes. It's written as interpretation for first order variables, interpretation for second order variables, and then you can write out.
Are you taking only subsets of this set?
Correct. So di are all so di are all subsets of 1 to k.
So monadic.
So that is why this is monadic second order. Monadic second order. Second order because you've got something more than quantification over elements. Monadic because it's only over sets of second order logic of order. Because it's about quantification. So it's really monadic second order logic over sequences. So I can now talk about this model. And notice that the semantics is exactly what you would expect. Right? In this model, A of x holds. If you look at the interpretation for x, that will give you a position, let's say position 5, and if A occurs in position 5, that you will get 2. And when you look at little x, an element of big X, look at the interpretation for little x, that will give you a position, big X will give you a subset, check if that element is there. That's when x equals y holds in the model if the assignment for x is the same as the assignment for y. X is less than y, well this is a position, check that, one is less than the other in the standard ordering. Negation alpha holds in the model, alpha doesn't hold in the model, alpha or beta holds in the model, if one of them, either alpha holds or beta holds. There exists x alpha holds if consider for some position within 1 to k, call it L, right? Consider the variant of the model where everything takes the same except that this particular variable is assigned L, and in that model alpha, there exists one. There exists big X alpha holds, if there is a subset you can find, such that look at the assignment where exactly in that position put that particular subset, and with that assignment alpha. Now, this is really an exercise in giving semantics or logic. If this is the intention, you can look at, if you take the notes and look at the page 16, that gives you precisely all these things. I don't want to write it down. You have the notes with you. Please take a look. So please pull out the notes so that I can refer to all these elements. So, what are the kind of things now that are expressible in this? Now, yesterday we saw, we didn't see that, but it was similar, and it came out repeatedly in Kamal's talk, and what Somnath kept pointing out was something as simple as the property of evenness is not first order defined. Now, there is a little, so what do I mean by that? Let me write it like this. So let sigma be AB. So L is the set of all W belonging to sigma star such that the length of W is even. Right? All even lengths. I don't worry about A's and B's. I look at all words. Right? Now L is clearly recognizable. How? Consider a little automaton which says whatever I look at my input and I keep counting the length. I start with 0. So the current length that I have counted so far is currently even. This is one state. I always find it nice to give names to states. And then once a letter comes, I go to currently odd. And then another letter comes, I go back to E. That's it. And this is also the final state. It's an easy exercise to see that this automaton, note that the transition functions are all correctly defined for every state and every letter you are saying which is the next one, and this gives you even length strings. Yeah? So it's easy to see that L is recognizable. But if you now do the transition monoid, the monoid corresponding to this, write down your delta epsilon, delta A, delta B, delta AA, AB, etc., etc., you will find that it contains a non-trivial group. You write the monoid, very easy to see that this better be a group. After all, this is the multiplication. Right? And so you will find that A squared equals A4 equals so on. Yeah? So this contains a group, and once Kamal completes the theorem, you will see that therefore it is not first order designs. Now, this as I want is a complicated proof, and he's going through some. Okay? So, but then, if this theorem were true, of course you can define it in a first order in monadic second order. How would you use monadic second order logic to define even length? So this is the theorem. So first, let's see what kind of formulas you would write. Well, I want to talk about the length being even, right? So I start with, maybe I can write order even. There exists some set x such that min is an x, max is not an x, and for all x, for all y, if y is a successor of x, then x belongs to x if and only if y does not belong to x. Yeah? So this is a way of saying that I have got so this says that I am able to collect all the even positions. I am counting from 0. So this is one way of getting parity. So if you now look at all sentences, right, all words which make this true, now it's consider the other automatons that we looked at. AA. Yeah, this was the one which had the automatons of this kind. So this is not AB power n but A power n, and this also Kamal went through the details, and you saw that there is a non-trivial group contained in the monoid. This is something that we saw this morning. And so, how would you write a sentence in monadic second order logic for it? That's a good exercise, right? You've already seen. There's already formula on the board. What about, well, we have already seen first order versions. So I don't want to spend too much time on the examples, but how would you go about proving this theorem? Let me straight away get into the how we're going to prove. But before that, I want to make one small, very important thing. Yesterday, if you remember how we came up with this idea of an automata, what was the idea? You had some events. So, some events. So, you are talking about a process, and you are talking about a mechanism which observes the process, records some things, puts it in its memory. And we said there are m registers, which each of which can hold some boundedly many values, right? So, the setup of some finite value space, and the configuration is actually a tuple of values. And at any point of time when an event occurs, you perform certain conditions, and when you perform some condition, if this condition holds, you update your counters registers in some particular way. Right? Remember, this is how I said, I can think of an instruction then as a triple. says when this event occurs, checks for some conditions, and depending on which condition, you perform some update. Right? And this we abstracted out. We said that as long as you mention there are only finitely many possibilities, you get around this. But something is going on here. If I take this, something that came up in the discussion again and again, maybe for when two different conditions hold, right? And if two different conditions hold, and you perform different updates, in which case the resulting state of the system on the same event would be two different results, right? Now, let me quickly go over this. I don't want to spend more time on this. Yesterday I gave you the kind of background on this. You can go deeper into the detail in the very same language of observations, processes, and come up with the same thing. There is one reason then to consider in the formulation of automata, which we said is a map, the tuple of this kind over sigma or T, right? On the same event occurrence, your delta, instead of thinking of it as a map, Q, what is quite natural to think of is non-determinism, where when the same event occurs, right, at a certain level of abstraction, at the level of abstraction that I am talking about, the same event occurs that on the different conditions hold, and therefore I take different actions. Therefore, the resulting state can be not uniquely determined, but it could be any one of them. So, one way of thinking of this is actually delta A as a map to 2 order. This is really where non-determinism really comes. It's just that at the level of abstraction that I am looking at, you can't tell when the event occurs what is going to be the resulting state. This is very important and I've seen lots of confusion about the difference between non-determinism and probabilistic transitions and, automaton choosing some particular state and so on. So it's not that. So at a more refined level of abstraction, you actually figure out, because of this condition, I'm going to this or this. But at the level of abstraction that we are picking, we're just looking at all of them as one, and therefore you want to consider. So I prefer this notation. So you think of this as a subset of Q cross Q. So delta A you think of as a transition. So this is a more general definition of automata. So, and these are, so an automaton is Q is a finite set of states, and delta A is a subset of Q cross Q, sigma I and S. If you think of it this way, but then what is delta W? Remember, we lifted this transition on a single event to a transition over a sequence. We defined this as a map from Q to Q earlier. But now once again, this also can be defined as a relation. How do you do that? Now there is an even simpler way of thinking about it. Look at the graph of this automaton, right? So you have some bunch of states, we call them initial states, and you have some bunch of states which we call final states. And basically what you are saying is that there is a path from here. So if W is of the form A1 to A, there is a W labeled path in this graph from some initial state to A1. Again, refer to the notes for the formal definition. You will see that this naturally generalizes the definition that you had earlier. You take this word, so you start with any of the states. Earlier you had a function that gave you a single path. Now you've got a whole lot of multiple paths. You take all the states that are reachable using these, and you want to ensure that its intersection with F is non-empty. This generalizes the notion of language FM. So language FM is all those words in sigma star on which there is a delta gives a path, gives a W path from I to X. So non-deterministic automata are very natural from the way we were. In fact, I was hoping somebody would point out that yesterday I kept saying that, okay, on the same event, different conditions can hold, and how do you pick which one? And it's a non-deterministic choice that you say you pick one of them. And if you actually formalize all this, is a picture. And that's the reason why I put I and F as both as subsets. They're both the relations. Anyway, so moving past that, but then are these, so now we talk about the particular kind of automata that we talked about, deterministic automata, are a special class where the relation that you have defined happens to be a function. And indeed, the initial state is single relation. So this is a particular subclass that you get, deterministic. So now you can talk about languages that are recognizable in general and those that are recognizable by the deterministic subclass. And there is a very nice theorem, again you can see in the notes. Theorem which says that theorem of Rabin and Scott, if L is recognized by a possibly non-deterministic automaton, then it's recognized by determinism. And the proof is by what is called the subset construction. Again, you refer to the notes, given the complete proof. And what is the idea? Look at the set of states of this automaton, an element, and these form the sets of the automaton that you are considering. So you take the non-deterministic automaton, consider subsets of states, and talk about going from one set to another via that gives you actually here. Now this of course causes an exponential blow because you take an automaton A and you are considering an equivalent deterministic automaton B, and the number of states of B is exponential in the number of states of A, and that is unavoidable, is also discussed in the notes without a proof, but there is some hint also to you might do. So something very interesting is going on. So non-determinism is something that is convenient, it is not inevitable. You can remove non-determinism, but the price that you pay is combinatorial. There is some cost you pay, which is very good. But it's a very important lesson that recurs in theory of computation. What's the advantage of non-determinism apart from those abstract benefits that we have? Well, proofs become very easy, which is always very good, right? For instance, if I have this definition in front of me, it's very easy to see that recognizable languages are closed under a unit. Well, suppose L1 is recognized by automaton A1 and L2 is recognized by automaton A2. What about L1 union L2? Well, simply take the disjoint union of the two sets. This is a relation on Q1, delta 2 is a relation on Q2. Take the relational union of the two. Take I1 union I2, F1 union F2, everything goes through, and this is exactly what you would expect. And that resulting automaton, and that is I think there somewhere on some page. I think you can see. There's no picture for that. But yeah, recognizing languages are closed under Boolean operations, so this one talks about. This theorem immediately gives you a very nice corollary saying that recognizable languages are closed under complementation. Why is that? Suppose L is recognized by a deterministic automaton. Right? Yesterday we said something, I pointed this out, and think about this. In a deterministic automaton, given a word starting from a unique initial state, you end up in one state, right? Some few, this is the final state. Right? Now, supposing I want to recognize the complement of L, what do? Suppose L is recognized by L by this is now a singleton set, let me write it not F, and this is deterministic. Now consider what I call M bar, Q, delta, same automaton, except that I am taking Q minus X. Right? It's an E. Yeah? It's Q minus X. It's very easy to see then that this automaton recognizes exactly the complement of X. And now, since I know that it doesn't matter what automaton that I start with, I can always consider an equivalent deterministic automaton. You give me a recognizable language, possibly by a non-deterministic automaton, construct the equivalent deterministic automaton, and then take the complement. You've got it. This is also a general automaton. So once you know that they are closed under Boolean operations. Another very interesting and simple thing that you see is that recognizable languages are closed under projections. By which I mean, suppose my sigma was given as suppose my events or alphabet had products. So my transitions are all of the form I am on Q on some pair AB, I go to Q prime. Right? What I can do, you understand, right? You just let my letters have some product structure. The Cartesian product. What is the projection of this automaton to the first component? Take every such transition and rewrite it as throw away the second component. Right? And that's it. Now, this L is a subset of sequences over pairs. The projection of L to the first component are simply the sequences where you are taking the first component. Right? And this is exactly the language. So, it's closed under projection. And once you have got a recognizable languages that are closed under Boolean operations and projections, a big part of one direction of this theorem is true. Supposing I can show, I want to show that if L is definable by a sentence in this logic, I want to show it's recognizable. Right? This is the one direction of the proof, where I want to see that my language, you give me a language defined by a logical sentence. I take this sentence, I look at its models. Remember that those models there's no issue of free variables, it's only these structures. Right? So it just works. And I want to say that this collection of words is recognizable by an automaton. So I have to build an automaton. Now, in logic, like in automata, sentences have very nice structure, which is an inductive structure. I can do induction on the structure of the sentence that you have given me. Right? So, what I can do is to try to construct atomic formulas will take a little bit of effort. We will see. Somehow I have to construct automata corresponding to atomic formulas. Supposing I manage to do that. Right? Then, when I get to the induction step, what do I need to do? Well, alpha is already given by an automaton. Well, I was saying it for words, now there are free variables. Whatever. Free variables always create some pain in logic, right? But we know that that's a little ant bite that you have to bear. for the greater joy of doing finally arriving at sentences. So we'll do that. Bit of bookkeeping and you can take care of it. So alpha is inductively given by a recognizable language, but recognizable languages are closer to complement. Negation alpha is all those words which are precisely the complement of this language. We have two. This is exactly closure under union. This is closure under projection. This is closure under slightly more messy projection. We'll get it. But it's also another kind of projection. So closure under Boolean combinations and projection already gives you one direction of. So in particular, if I wanted to show that, if I wanted to show only this part without the second order, right? If I were looking at the logic that we began with, which is first order logic, right? If L is a language is defined by a first order sentence, showing that it's recognizable, is something that once we fix atomic formulas and how that is done, you will see it. 5 minutes, you'll see that the proof goes. But of course, for proving the theorem that Kamal is after, you have to show that it's recognizable by a counter-free automata. That takes more work. Okay. Now, this is something that we can't do in this short time. But suddenly, it's anything that's definable in first order theory of order is definable by an automaton. Is very easy. So I have to tell you for this direction of the proof, I have to say what to do about the atomic formulas, and I have to say what to do about the set formulas. We'll get to it. But fair amount of work gets done as you go. Now, what about the other direction? The other direction says that L is recognizable. I'm sorry. Yeah, that means you give me an automaton, right? Deterministic automaton doesn't matter. I have to write a first, a sentence in monadic second order logic that gives you exactly whose models are exactly those words. Right? How do I do that? But now this picture already suggests what is going on. Right? That picture is very nice. Thinking of it as a path in the graph, right, tells you that certain coding up is possible. Kind of coding up that Somnanda mentioned. Right? We're used to doing this. Coding of runs of machines and logic in some particular way. You just follow the norm and exactly get what you need. So look at what is going on. So I take a word W. Suppose this belongs to the language of the automaton. Then I know that, so this word I am actually writing as positions 1 to k, which happens to be labeled by A1 to AK. So let me call it ABB, ABB, some labels are there, which is actually the structure, right? What is the structure? These numbers, and you are labeling them, which is what I am writing down. The order I don't have to write down. This is the picture. Now, what does it mean that this word is accepted by the automaton? You start with some initial state. So let me call it Q0, which belongs to I. On reading the letter A, the automaton is able to move to Q1. Right? Q0, Q1 is in the relation delta A. Right? And on reading this, it goes to Q2 and so on, and it arrives in Qk, which belongs to F. What does this belongs to I and belongs to F and so on that we are talking about? We have this in our language now. We have this in our language now. So it's no problem at all. We looked at these letters. From these we built sets, which we called PA and PB. We can follow the same logic and build sets of positions where, so let me take Q0. Right? Let me build a set X0 as all positions where Q0 occurs. Right? And this is there will be repetitions in general. Right? Exactly like ABBBA, this is actually going to from Q0, Q1, Q1, Q2, Q1, Q0, let me say, the 3 states are enough. Right? So Q0, so X1 are all positions where Q1 occurs. X2 are all positions where Q2 occurs. That's all. There are Only 3 states in my automaton and I write. So the formula that I am looking for looks something like this. Suppose so we said we are given the del is recognizable. So there is some automaton M that is given to me, Q delta I sigma, and let's say that Q is Q1 to QL. Lots of indices around, so I have to be a little careful. Right? K is the length of the word that I am working with. M is the number of first order variables that are free for me in the formula. N is the number of second order free that are variables. So a lot of bookkeeping is needed. Please have some patience. So, and as far as I am concerned, what do I care? I might as well think of the states as 1 to L. U1 to 2. So, I am going to say there exists x1, so there exists xl. That's what I want to say. Right? There are positions, there are sets of positions which are labeled by some fellow 1, labeled by 2. So, my labeling of the word, remember, what is this 1 to k that we started with? This is a linear order. Right? This is my prefix. Fragment, initial fragment of the natural numbers. And I am labeling them with PA and PB, and I am similarly labeling with X0, X1. That's what it is. So, and I want to say that these form states, right? I want to say that these are really labels of states of my automaton, and then I want to say that something happens initially, and something happens when you take a transition, and something else. I have to write formulas for all these. And lo and behold, please move to page 18 of the notes. You don't have to write. If you save time, you can actually go for lunch. Right? So look at the formula saying states. What is the formula saying for states? For all x, x is in one of the states. For all x, or over I equal to 1 to L, xi. Right? You have to be in one of the states, and you can't be in 2 states simultaneously. Right? And over, so and over j not equal to I. I'm sorry, x belongs to not x. Lots of better. That's it. I am in, so the formula states this, I am in exactly one of the states. You give me any position, it belongs to exactly one of the states. What does init says? Init says I will start with one of the initial states. That is what it says. If you take or over j in the set I, right? I stands for all the initial states. Right? So or over j in I, min belongs to xj. What is the final? Well, final we'll get to. What is the transition thing? For all x, for all y, if y is a successor of x, y is a successor position of x, that means what? If you happen to label, right? That's what it's saying. You take or over iaj belonging to delta, right? Look at the triple in the delta. Look at I to j of this form. If you have happened to have labeled the exit position with I, right? Then I should be labeling the jth position with y, and the label that you have on this particular one. In the notes it is called QA, you call it PA. That's it. This is a very natural coding. You are saying I am tiling with triples that merge. And then final. Now final looks a little weird. You would have expected to say or over j belonging to f, max of this. Unfortunately, this is the mismatch between the length of the word and the length of the round. Right? You need one more. Right? The length of the word is k. The triples that I am matching, I have a k plus 1 length. So there is a slightly weird formula that you hangs around there. So please go over it and make sure that this is okay. Actually, it works. So that's why I said you have to do some. That's it. That sentence, now we can show that a word is accepted by this automaton if and only if it is satisfied by this. It satisfies this sentence. And there is a proof outline that is given out here. You follow that. There is a nice inductive proof, and you are true with this part. There are some remarks which I will come to. What about the other direction? The other direction, as I said, we have some work to do. What is the work to do? Well, I want to start with a sentence and I want to construct an automaton for it. Right? An automaton that runs over those structures. Right? If I take the sentence, its models are the structures. What are structures? This over the linear order, I have some A labels. That's what it is. Right? Some sigma labeled linear order on which I have to run my automaton, which I can think of as a word over sigma. But unfortunately, this is not a sentence. If I am going to do the proof by induction on the structure of formula, I have to consider a formula. And for a formula, the model is not just a structure, but assignment to variables. Right? Remember that for a formula with 3 variables, the model looks like this. Now I have to construct an automaton that runs on these. How do I do that? And that's very simple. So I do a coding of the model as well. Yeah. So this is how I do it. So I start with, supposing there is a word W of length K. A1, A. So on this I have, for let's say that alphabet is AB. I have one row for A, one row for B. What is this predicate A doing? It tells me which are all the positions where it occurs. So let me think of it as a bit vector. 0, 1, 1, 0, 1, 1. This means 0 are all the positions where A doesn't occur, 1 are all the rows. Right? So this is some bit vector 1, 0, 1. Now, what?
One is occurring at both positions?
Yeah, of course you have to make sure, and that is something that automaton can do very easily. So you have to make sure that exactly one of them. So this is in fact a complement. It's in fact a complement, so there is nothing else to do. Yeah. If A doesn't occur, B has to occur, right? You can't have more. And then, now what about my first order variables x1 to xn? Now this is a position, right? So that position occurs somewhere here, right? So basically it means it will be something else. 0, 0, 0, 0, 0, 1. And remember, it has to be one of them. So this is a bit vector where a 1 occurs in exactly one position. And what about these fellows? Well, this is some bit vector, that's all, I don't care. So this is some 0, 1, 0, 1, 0, and so on, and this is 1, 0, 0, 0, 0, 1. So now consider the alphabet, and this is what. So the alphabet that I consider is not sigma. By move over to a larger alphabet, which I call sigma V, which is sigma cross first order variables called second order variables. For all of them, you put 0, 1. Now, again, if you look at, please do me a favor, look at page 19, and you start with let phi be of, if you see the second paragraph, it says, okay, you start with first order variables, second order variables, V phi is given as F phi union S phi. F phi is all the first order variables, S phi. Now, what I have called EV, E is sigma. E cross F phi. So you have, for all of them, you have a 0 or 1. Now, I look at sequences over E, sigma V now. My automaton runs on these. What is the first thing it has to check? It has to check that a word that I am looking at is actually a legal word. What's a legal word? Well, among the letters, exactly one of them occurs, and the first order variables occur exactly in one position. Now, here I've already made the assumption that you are given legal words, so that part is not a problem. But I have to make sure that for first order variables, it occurs exactly in one position. Look at the automaton in figure 6 that accepts exactly the legal sequence. You start on the state. Now, what is the kind of words, what is the alphabet that you are looking at? It's going to be A followed by F. F is giving the bit vector. So, you check that Fx equals 1. So, you keep looking for that exit variable becoming 1. Until then, so you keep looping in the initial state until that thing becomes 1. And then you are willing to accept anything as long as Fx is 0. This is it. And these are non-deterministic automata, so I don't have to even make it good. So this ensures that the legal sequences are recognizable. After this, whatever I do, I always take intersection with legal sequences. I know that regular, recognizable languages are closed under intersection, and therefore I can always do it. That's right. Now, I have to now construct automata of this kind for all the atomic formulas. And you see page 20. The top figure 7 is an automaton for PA of x. What is it supposed to do? It's supposed to check that somewhere a position A occurs. Since I'm going to take intersection with legal sequences, I just have to check for A occurring somewhere. That's all it does. F of x is 1. Okay. What does that mean? Where you are seeing an A, this position, right? The exit position is labeled A. That's what it says. So when you are seeing an A, f of x is also equal to 1. You always check, take intersection with B. What about the automaton for equality? The next one. Figure 8 is the automaton. What it does is it keeps walking around. It makes sure that when f of x is 1, f of y is also 1. That's it. Take intersection. Now, this power of non-determinism is something that's used inherently in all these kind of pictures. Right? Otherwise, for a deterministic automaton, this would be very difficult. And what about x less than y? Well, look at the automaton in figure 9. It keeps looking for x becoming 1, and then it goes into a state where it starts looking for y becoming 1. And after that, it's willing to accept it. Right? So you have to make, so here this ensures that x is strictly less than 1. And what about little x being a member of big X? Well, same thing. This automaton keeps going around. Anytime that little x becomes 1, it's checking that big X is 1 as well. You know that little x is going to become 1 exactly at one position. I just have to make sure that the big X at that point is also having 1. So this takes care of all the atomic formulas. We have already said that it's closed under all these. What about the second order modifier? It's no problem at all. Again, what is the automaton supposed to do? You look at the labels of the automaton. Wherever the big X becomes 1, erase those two. That's all that you do. Right? And you will see that you just have to discard the jth component of this automaton. Because there exists xj means that I am projecting out of this row. Right? So this automaton has big tuple on its labels. In the example for projection, I said pair, just a pair. Right? This is going to be something of length m plus n plus 1. But the second order projection is also projection on some particular power. Just remove that. So that's it. So it gives you a neat construction, and you are through showing that L is satisfiable. So some important remarks, even though it's time, is that one is that what is the size of the automaton that you construct? Right? Given any sentence, I said that you construct an automaton. Now, how big is that automaton? Certainly it has to be big, because remember, every time we had a negation, we started with something that was non-deterministic, looked at the equivalent deterministic one, which I said has an exponential block, and then you complement it. So every negation gives you an exponent. it mean it's exponential? Sadly, no. Because remember that for all is defined in terms of negation of their existence, right? So every time you have a quantifier alternation, you're going to have an exponent coming in. So what you get is 2 power 2 power 2 power 2 power m, where the height of the tower is given by the quantifier alternation of the interform. And there's a beautiful theorem of Mayer and Stockmayer in 1972, another paper, must-read paper, which shows that this non-elementary blow-up is unavoidable. So it's unavoidable. And this is something that, and another very important thing to note is that we started with an automata. Now look at what is going on. We also have a corollary to this, that MSO and existential MSO are exactly equal in specificational power. Because suppose something, consider any language defined by an MSO sentence, we have already shown that it can be defined by a sentence of this kind, where this is first order. You look at the formulas. So that means that monadic second order logic has a normal form, where you give me any formula, there is a prenex form that I can write it in, where I can eliminate the universal quantifiers. So this is what is called the automata normal form, because it's very hard to try to directly prove that.
Doesn't it reduce the tower then?
It doesn't. For first order logic itself, it's not eliminated.
Oh.
Because the complement and there exists.
Okay.
So FO already is not elementary, so it doesn't matter. So this is a very nice logical result. If you think about it, you're giving a normal form for this logic, and that normal form is highly non-obvious. And in fact, I have also said that for every state I have put a second order quantifier, right? L second order quantifier. But actually, if you are the kind who worry about it and think carefully, if L is the number of states of the automaton, log L to the base 2 will suffice. So you can, control the measure in some sense, but these are all known as automata anyway. But what about this? Finally, as I said, you've established some correspondence between these sentences that describe behavior in a particular way. As I said, in a process term, and these memory structures. Automata theory is the study of memory structures. It's a beautiful statement by Ravi in sometime in 1960. And so it's a way of looking at memory. Right? That's what I said. But this duality is very interesting. Even though the same behavior you can specify in terms of automata or in terms of logic. Sentences, what is the trade-off here? Trade-off is really in terms of complexity. I've already said that these sentences are very, very concise. They pack enormous amount of information. That's what is told to you by saying if I look at the automaton for it, that can have 2 power 2 power 2 power 2 power size. Right? So the order information that is given here is highly concise. The existential quantifier, like I said in the case of that arithmetical statement yesterday, that you can write something like there exists x such that x times x is 1024, finding x is very hard. Right? Similar thing happens here. So the existential quantifier is really packed a punch. It carries an enormous amount of it. But what is going on is really compositionality. Right? In logic, compositionality comes for free. Right? Negation alpha carries the same cost as alpha. In automata, when you look at complementation, carries an exponential cost, right? And operations on automata, if you look at, right, you can build an algebra of automata. You can look at various operations. There are very nice operations that you can consider. Beauty has developed a very nice theory, and so algorithms come for free out there, checking for whether a given non-deterministic automaton accepts a word or not. Right? Roughly the satisfiability kind of question. There is some model at all. Right? Now, that's easy in automata. In fact, it's linear in the same way. Here, an algorithm that checks whether alpha is satisfiable, there is huge cost. Right? So, there are dual descriptions that say the same thing, but concise in very different ways. Minimization is a very natural question to ask, and you can solve. For automata, minimizing a formula is very, very difficult even to actually conceptualize what you mean by that, what are the logical resources you are minimizing on, and whether there exists coming up with algorithms is hard. Right? So there are two ways of saying the same thing, but carry very different connotations. And last word is that the processes, when you think of processes, I said, when you have different possibilities on the same event, you think of this as making a choice, a non-deterministic choice. You need not. You can also represent these processes exactly the way that I was building up and build trees, right? You just record all the choices that you make along the way, and rather than looking at sequences, you can look at trees, right? It's a very natural description, so you can talk about language of trees, and you can talk about automata that run on trees. And this entire picture that I talked about, instead of language of words, you can lift the language of trees. And there are nice theorems of the appropriate kind. You can also say that instead of one person making observation and looking at these sequences, let's say two people make observations and record and communicate. Right? So you can actually build theory of processes based on that. You get partial orders, the linear orders. Okay. And you can talk about automata that run on partial orders. And you can talk about a logic that is, look at this logic. How does it matter whether you interpret the order relation as a linear order or a tree or a partial order? Right? And you can, with just some bit of work you can define. Fortunately, coming up with an equivalence of this kind over partial orders turns out to be really hard. So on sequences, the thing is beautifully developed from the 70s. By 80s, we could see what to do with trees earlier, but at least fair amount of work. Partial orders is still, I would say, current research. Now, what I'm saying is that the paradigm is very similar. You can take off in very many different directions. You can also go down instead of saying finite sequences, I look at infinite sequences, languages over infinite words, infinite automata over infinite words, and the logic doesn't care. Who cares if the model? It looks exactly the same. Except that min is definable, max is not definable, it doesn't exist. That's all. Right? Logic remains exactly the same. Beauty's theorem lives very neatly. Beauty proved the theorem and that settled a very nice problem that Tarski had posed, right? As I said, there's a nice model theoretic ways of building up these. And logics over infinite trees that Rabin settled in 1980. And over infinite partial orders, we don't. Sorry, very much. Thank you.
Thank you, sir, for this interesting talk. Any question?
Quick question. Slow question. Regular is determined reserved for R class being the same. Exactly. So, in fact, I never said if every language were recognizable, there is nothing interesting. There are lots of non-recognizable languages, and that's by showing that the R classes are included. And that's there in the notes.
Thank you very much, M. So I must mention, when we were planning about the school, I mailed him myself and mailed him a couple of times, and he always encouraged us that we should do, and he guided us in many ways. So really we are grateful to Professor Ramanujam, and thanks a lot for coming over here and giving the talks. So we have something.
It's by the same artist, Shorno, you can write it down, Shorno Potua, Shorno Chitrakar. They call themselves Chitrakar. Shorno is a woman, so she was here in this, as I said before, she was in the workshop in Kolkata, and she drew all these pictures.
So thank you also.